Hello, we are discussing the design and implementation of an ECG peak detection circuit. The ECG is a widely used diagnostic tool in biomedical engineering and clinical medicine for monitoring the electrical activity of the heart. The ECG signal provides information about the rhythmic activity and overall health of the heart, with particular emphasis on identifying features such as P wave, QRS complex, and T wave. Among these, RP within the QRS complex is of critical importance as it serves as a key marker for determining heart rate and performing real-time monitoring of cardiac function. Here we are doing the same. We have 5 stages in our circuit. The first stage is the amplification stage. The magnitude of the voltage received from the electrodes is very low. It is up to 5 millivolts. So we need to amplify this. So we have roughly amplified this by a value of 100, and as we can see, the green signal denotes the input and the yellow signal denotes the output of the inverting amplifier. The next stage is the subtractor setting. The subtractor stage is implemented as a differential amplifier using an op-amp in the standard configuration with equal resistors to achieve unity gain. Its main function is to remove common mode noise present on both input lines, such as 50 Hz power line interference or motion-induced voltage shifts, while preserving the actual differential ECG signal, which carries meaningful cardiac information. Remarks. This stage is crucial for improving the signal-to-noise ratio before filtering. It does not amplify the ECG signal, but it cleans it by rejecting noise that appears equally on both inputs. This is the output of the subtractor circuit.
So, after the subtractor circuit, these three MOSFETs consist of our 6th order Butterworth low-pass filter. A low-pass filtering stage is designed to attenuate high-frequency noise and stabilize the baseline of the ECG signal. It uses a cascade of 3, 1, 2 and 3 second order Butterworth filters, resulting in a 6th order filter with a sharp cutoff of 35 Hz. This cutoff frequency is chosen to retain the primary frequency of interest in the ECG signal, while effectively filtering out the power line interference, which is of 50 Hz, and the other high frequency noises which we do not want. A Butterworth filter is chosen for its maximally flat frequency response in the passband, ensuring minimal signal distortion, which is very important when we are dealing with ECG signals. It provides a smooth roll-off beyond the cutoff frequency, effectively rejecting noise without introducing ripples in the passband or stopband. This makes it ideal for applications like ECG signal processing, where maintaining signal integrity is critical. While designing a Butterworth filter, we consider the nodal analysis of second order active low pass. We analyze the circuit using KCL at nodes, and then assuming the ideal op-amp conditions, we basically calculate the values of omega C, which is our cutoff angular frequency, by using the value of C1, C2 and R2, R3, which we have used in each circuit. The resistors R1, R2 about which we were talking are these 1 and 2, and these capacitors about which we are talking is this C3 and C4. So this whole comprises of our 2nd order Butterworth filter. While talking about the cutoff frequency and the Bode plot frequency response of the low pass filter, we can see that this green line represents the output, or we can say the frequency response after the first low pass. This pink line represents the output or the frequency response after the second low pass, and the red one represents after the third low pass. And this red hence results into the net frequency response which we have after 3 low pass filters. This is the frequency response after the third low pass which we are getting according to our DSO from the hardware circuit which we have made. And this is our time domain output after the low pass filter. The green one represents the raw ECG signal which was taken into our circuit as an input, and the yellow one represents the output, the denoise, the signal after denoising which we are getting after our low pass filter as an output.
After the low pass filtering, we now move on to the differentiator circuit. This stage emphasizes rapid changes in the signal, which are characteristic of the QRS complex. By performing a differentiation operation, the high frequency components corresponding to rapid changes in the ECG signal are observed, facilitating R peak detection. By using KCL, we can easily say that the output is the differentiation of the input. But we can also observe that this circuit acts as a high pass filter. Here is the frequency response of the high pass filter, and here is the time domain response of the output of the differentiator circuit. After differentiation, the signal is amplified by a gain stage to bring it to an appropriate level for threshold comparison. This gain stage also inverts the signal, preparing it for the subsequent threshold detection stage. This is the output of the final gain stage.
The processed signal now goes into the Arduino, and thus we have displayed the BPM by finding the peaks, setting a threshold.